In this presentation, I will present my bachelor thesis. The topic is classification and analysis of pore in laser powder bed fusion. First of all, porosity in the laser powder bed fusion process can originate from three main sources. We can have gas porosity, lack of fusion, and melt-point instability. Using the geometric parameters illustrated in the previous slide, the pores detected through X-ray computed tomography were classified. For each pore, the value of the three geometric parameters were determined, and the pores were classified as spherical if they had compactness greater than 0.4, and sphericity and binding box factor greater than 0.6. Following this classification, spherical pores were further divided into three subclasses, A, B, and C, based on the diameter increasing from class A to class C. Subsequently, it is possible to see the spatial position of the pore. In this 3D representation, different colors represent different classes of pores. We now move on the identification of cluster. To achieve this, the DB-scan algorithm was adopted. The pore coordinates an epsilon neighborhood and a minimum number of pore n that must be present in the neighborhood to define the pore as belonging to a cluster were provided as input. The cluster present in the analyzed cylinder were then illustrated in the three dimension. In the representation, an epsilon of 10 VOX and n equal to 3 were used. Finally, the centroid of the cluster were identified by calculating the average value of the coordinates of the point belonging to the same cluster. It is possible to see in this animation the pore in blue and the centroid of the cluster in red. In conclusion, it has been possible to classify the pore based on their geometry and define their spatial distribution in the analyzed spacement. We observed that they tend to concentrate along the edge, likely due to high thermal gradients and gas entrapment caused by rapid cooling. Furthermore, by leveraging the DB-scan algorithm, we identified clusters of porosity, which are particularly critical as they represent a gray zone for stress intensification, ultimately compromising the mechanical properties of the material. This insight enables us to compare various thermal porosity treatment techniques to determine which provide the most beneficial effect. Additionally, has been possible to compare process parameters such as laser speed and power, as they significantly influence pore formation and distribution. Understanding this factor is crucial for optimizing the additive manufacturing process and enhancing the final product quality. The detailed characterization of the pore has also provided crucial insight into their impact on key mechanical properties such as fatigue resistance. Indeed, porosity clusters play a critical role in determining the structural integrity of a component. Among the defects analyzed, surface defects were found to be more determinantal than internal ones, as they induce higher stress concentration.